continue chapter 9 that talks about alkynes of David Klein's textbook. Now on to 9.3, which is the acidity of acetylene and terminal alkynes. Acetylene is an important molecule because we can use it for acetylide alkylation, which we will talk about later. But to get to the first point, we need to discuss what the pK of acetylene is and why it's important. Acetylene's acidity relative to ethylene and ethane. So how does the pK compare? Well, acetylene is much more acidic with the pK of 25. Acetylene is 44, and whereas ethane is 50. This is significant because we learned from the previous chapters on chapter 7 that strong acids prefer to shift the equilibrium towards weak bases. Strong acids shift equilibrium towards its conjugate. So it used to be part of the acid. That's what conjugate means. It used to be like part of the reactant I'm talking about, and it's a conjugate base. So strong acids make weak conjugate bases when it shifts the equilibrium forward, and so acetylene. So that's why we talk about acetylene, because its pK is the lowest out of all, and it shifts the equilibrium towards its weak conjugate base, and perfect for acetylide alkylation, which we will talk about later. Now, so point 2. So adding on, when we use a strong base to deprotonate acetylene, strong base to deprotonate acetylene. Now we're talking about strong base. Strong base shift the equilibrium forward towards weak conjugate acids. So towards the side with, and so that's why we shift towards the side. So if we react a strong base with acetylene, we will get the side with favored side with the weak conjugate acid, and so conjugate base of the acetylene, which is what we want, because that looks like kind of like this and has a negative charge. That's what we can use to react later. That's why it's important. Point number 3 is that what if we used hydroxide? What if we used hydroxide as the base in a typical like alkyl or any reaction? Well, if you use OH, well, this is not a good option, because hydroxide ion is considered a weak stable base. So things like NaOH, this is like ionic, so this will be +1 minus. This is basically that, and so that is considered weak stable base. Well, we can't use this again to react with acetylene to make it into an acetylene conjugate base, which is what we want here, because this is a weak base, and we learned that equilibrium shifts always to the weak base. So if we were to react this with acetylene, then the reaction will shift back towards itself. That's not what we want. So what are good options? So why you can't use NaOH is because it's a weak stable base. We need a strong base. So what are our strong bases that we need for acetylide alkylation? Well, that point 4. Point 4 is that the conjugate base of terminal alkyne can only be formed when reacted with what? So this is basically asking what strong acids, or sorry, strong bases do we need to make the acetylide ion we really want? Well, the good strong conjugate bases, strong bases include NH2. So we need strong bases to make the acetylide ion, acetylide conjugate base, conjugate base. And the good options include NaNH2, which is considered a strong base, or we could use like things like NaH. These are the couple of the many options we can use, but keep in mind that NaNH2 is very commonly used. And so what does this look like in practice? Well, basically, if we had a molecule like R, C, C, and then H, and then I would like B, bromine, and another bromine. If we reacted this with two equivalents of NaNH2, which is a strong base, and within NH3 solvent, this is just a solvent, then basically we want to form an alkyne, right? An alkyne. How is that possible? Well, NaNH2 is used for elimination. So we talked about like the beta here, so that's why we could form R, and then this is what it should look like. And so after that, note that we could use strong bases for elimination. That's why we have turned this into that. But also what we learned from above was that we could use strong bases to make the to deprotonate an alkyne to form an acetylene conjugate base, which looks like this. How do we do that? Well, we learned. So how's that possible? It's because it came from something like this. This is like the acetylene, and strong base basically will deprotonate this to turn into that, which is acetylene, which is that. So basically, this is the strong base as we just talked about, and that's why we this is another story. So basically, this is the elimination portion. Elimination, E2 elimination works with strong bases, and then from here, now we could use NH2 or the strong base. So NaH also works to deprotonate this, like we just learned above, to form this alkyne ion with the charge. So we call this the alkynide ion, and this is where we get it. This was, so far we were talking about 9.3. 9.4 is preparation of alkynes. So how do we prepare alkynes? We talked about the acidity of acetylene and terminal alkyne so far. This is considered a terminal alkyne. And now we talk about preparation of alkynes. Excuse me. This is on to point number 5. So how can alkynes or triple bonds be prepared from alkyl dihalides? So alkyl dihalides, something like so we got a bit ahead of ourselves. This is basically what it's talking about. Acetylide ions. Alkynes can be made from something that looks like this. Right. So we learned that something, let's say, how can we make something like this? Let's try this. Well, this can come from a dihalide. The dihalide would look something like this. And if we react it with two equivalents of strong base, like NaNH2, we can get this alkyne. Likewise, for part B, we could use, say, Cl, and use NaNH2. We're going to use excess and NH3. This is a solvent. NH3 is a solvent. And 2, we're going to use water to acid quench. And what do we get? So we can use elimination to answer this question. Or this is something, I think. Yes, this is what should we get. We should get. This cannot eliminate this direction because there's no hydrogens available, as it's all filled up by the carbons. Point number 6, part 9.5, 9.4 and 9.5 is reduction of alkynes. Now, this is point number 6. How do we form cis alkenes from alkynes? Well, cis alkenes can be used using molecular hydrogen and Lindelar's catalyst. So it should look like this in practice if we had something that looks like this, and if we used H2 and Lindelar's, we would get something like this. Notice we're talking about cis. Basically, it just means that both R groups are facing the same side, and so then that means the rest should be hydrogens pointing away. Cis just means both R groups on the same side, and we could do this with H2 and Lindelar's catalyst. However, what if we use just H2 and palladium, or PTC, PT, or then basically we'll just get alkynes. And so this is what we should get. Let me count. We had 1, 2, 3, 4. 1, 2, 3, 4. This is what we should get. It reduces. Reduction means just removing the double bond, or in other words, just making more hydrogens on the product attached to carbons. Speaking of another example, we can get something like this. And what if we used, again, the same example, H2 Lindelar's catalyst? We'll get something like this. R groups are on the same side. Now, point number 7, how do we form trans alkenes from alkynes? And why do we get 4 products? Including regioisomers and stereoisomers. Okay, to answer this question, you basically need to understand the mechanism of metal reduction. Now, basically, in order to do this, we said cis, we need H2 and Lindelar's catalyst, but transalkenes, this we will need NH3. Is it NH3? Sorry, yes, it's NH3. But more importantly, you'll need sodium solid and NH3 in liquid form. This is important because let's say we had something like this. We could use NaS and NH3, or this is ammonia. Let's switch it up. Ammonia. So it's ammonia. You could use ammonia or NaS or sodium in solid form to make it look like something like this. Notice the R groups are pointing opposite of each other. Now let's understand the mechanism of dissolving metal reduction. So onto the same molecule we see here, basically we will use fishhook arrows. This basically means one of the electrons will go in that direction and the other one will go here. What will it do? Basically the sodium solid will have one electron, and it will combine with this like that. And then where does it meet up? Well, basically so let's go like this. It'll meet up like that. So we will get something like this. These two electrons came from the combining sodium and the other fishhook arrow. And next, what will happen is we will continue on, and this is a negative here, so this will want to deprotonate something. That's where the ammonia comes in. Ammonia looks like this. Basically, it will want to fetch that hydrogen, kick it off the electrons there, and we will get continuing on hydrogen, and this will become NH2 with a negative charge. What is this called? NH2 looks like it's an amino radical. This is called an amino radical. We will form on the side product the amino radical for now, and we will still have that one electron. Now that one electron, it will react with another sodium solid with an one electron. Combine. What will it do? Basically what we just did above, form a lone pair with a negative charge, and this will want to, I would assume, react with another ammonia, deprotonate the hydrogen, kick it off to a nitrogen of the ammonia, and we will get our trans product. How do we know it's trans? Because the R groups are opposite each other. And on the side products, we will obviously have two amino radicals. And this should be our answer this is our mechanism for dissolving metal reduction. Now, to answer concept check 9.10, to answer 9.10, we don't need to do that. 9.11. So what will we do to make this into that? And what we will use to do this into that? Well, this is cis, this is trans. So we know for cis it will use H2. And what we'll use? H2 and Lindelars. We won't use H2 and PT/D because that won't reduce it into alkanes, which is too strong. Trans, we want sodium solid and ammonia in liquid form. That's very important. Okay, so we covered point number 7. Point number 8 is part of 9.6, hydrohalogenation of alkynes. What is the mechanism for hydrohalogenation of alkynes? Hydrohalogenation of alkynes might look something like this. You have an alkyne and you have HX, hydrohalogenation. We know the nucleophile will always be the double bond or the triple bond, or in this case, it might not be always, but it deprotonates that, pushes it off. Mechanism, this is the mechanism, and so it'll push it off. And then basically what we get here is, this is Markovnikov's, and so carbocation will form there. Hydrogen goes to just to fill up the less substituted. Carbocation goes on more substituted. And then basically this halogen will have a negative charge, and this will want to come here. This came to become that. And so we get this product. We get this. So proton transfer and nucleophilic attack. Now, point number 9. Let's say we had something like this reacted with 1 equivalence of HCl. What will we get? Learning from our mechanism, we learned that this is only about Markovnikov, so Markovnikov of the carbocation. So when we basically do this and deprotonate, it should look something like this. What I showed you here is trans, because these two R groups are opposite one another. Now they could be trans, and so then if we do that, it's important that it could be trans. Let's put it this way. It could be either be trans, and let's say the chloride attacked on this portion of the alkyne. What was it? Let's say the chloride attacked there, because that's where the carbocation formed. Then it would be that, and hydrogen goes here. And if it's the trans, then this is considered Z or Z, because we learned the R groups are opposite one another. And what if, so let's say the chloride still attacked on this portion of the alkyne because of the carbocation formation there, then we could get another form, right? Because even though this looks like that, we could get that. We could get that the two R groups are on the same side. If they are the same, this is sin, as in for E. This will be E. Sorry, I think this might be wrong. It might be wrong. I think it's saying this is Z, as in for same side, Z, same side, because the chloride and 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 ethane, the two biggest contributing functional groups are on the same side. This would be syn. Sorry, this would be syn, and this would be anti, right? This would be anti because this biggest functional groups are opposite another. Same side or Z, opposite. Now this part still holds true. The chloride still attacks on this portion of the molecule, and that's why we get that. Well, are these two the only products? Apparently not, because we learned that. Well, I think, sorry. Yes, for this, these are the only two products. However, let's say we changed up things a little bit. Let's say we got rid of that. This, because, again, sorry, let me undo it. What we dealt with so far, this is symmetrical. If we made it unsymmetrical, let's say this is just like a methyl group, what would look like it then? Basically, if that was just a methyl group, that means that it makes a room for regioselectivity. What do I mean by that? We said chloride could attack on this portion of the alkyne. Well, chlorine could also attack from there because carbocation could form on either side of alkynes. In alkenes, carbocations did have significance when dealing with Markovnikov, but with alkynes, it really doesn't matter because internal alkynes, you can't really have a favorability for carbocation. Well, in this case, it did because this is terminal, but this is internal, and because it's internal, we basically know that this will not be the case like as in this because to explain it, the Markovnikov will not apply for internal alkynes. So no mark, or sorry, do not think of that. But anyways, straight to the point. If the chloride attacks on this side here, then basically we could get chloride that looks like this. Then the ethane will go there. Now we could get the syn. Syn basically would look like where the methyl, this thing here, methyl was on the same side as chloride. This will be syn Z, and then we get the hydrogen. Or we could get, remember we still target the chloride on this portion of the alkyne here. If we do so, then chloride could go here, and the methyl we were talking about can go opposite, filling in the rest like this. If that's the case, then this is considered E, as in for opposite or anti. And so a total of, okay, let's clarify this again. This is opposite because methyl and chloride are opposite. Here is the same because both methyl and chloride are the same side. So we get a total of 4 products you could form when we're dealing with internal alkynes reacting in hydrohalogenation fashion. Now on to point number 10, which is still part of hydrohalogenation. Point number 10. So let's say we had a molecule that looks like this. And what if we reacted with HBr, hydrohalogenation, and ROR? This stands for hydrogen peroxide, or R just means extended alkyl groups. If this is the case, what will happen? Well, it turns out that in this case, anti-Markovnikov happens. As we mentioned earlier, this anti-Markovnikov or Markovnikov was only significant for terminal alkynes. Internal alkynes, it wouldn't really matter. Alkynes, I said, are triple bonds. Alkynes. This only matters for anti-mark for terminal alkynes. What will it look like then? Well, then in this case, the carbocation. If we try to think about the mechanism, we'll end up on the less anti-Markovnikov fashion. And so then the products would basically look like this. If we turn this into, reduce it into alkene, sorry, Br will go anti-Markovnikov fission. It's not the only product because, as we learned, it could form different stereoisomers. Now, what would this be? This would be trans. In other words, this would be like anti or E as in for opposite. But we could also get syn addition, which stands for Z, and this will basically look like 1, 2, 3, 4 syn because they're both on the same side. We get a mixture, probably favoring trans as we mentioned earlier because of less clashing in each other sterics of substituents. Now, on to conceptual check 9.13. If we had something that looked like, let's say we had a benzene ring and had 2 chloride groups and reacted with first with excess NaNH2 in an ammonia solution. Just have it correct. Yes, ammonia solution. And let's say for part 2, we reacted with water, and 3 we do the anti-Markovnikov addition, or anti-Markovnikov, what do you call it? Anti-Markovnikov, anti-Markovnikov addition with alkynes, right? Well, if you start off with this, we learn strong bases. Strong bases favor forward direction. It shifts the equilibrium forward. And when we're dealing with dihalides, and say this was excess strong base. In this case, the equilibrium basically will shift forward, and we will do an elimination. Now, if this was alpha and this was beta, and this was also beta, we mentioned there's no hydrogen here on the beta, so we can't do elimination that way. You can only do it this way. That's why we get, because it's excess, we'll do the elimination twice and get that alkyne. Alkynes you can't draw in a bent way, it has to be like straight, because sp hybridized it goes straight, I think. I don't know if this is sp hybridized. Yes, I think it's sp hybridized, but this is alpha and it goes straight. Now on to, that's part 1 and part 2, and on to anti-Markovnikov alkyne addition. This one, what will it do? HBr will go on the bromide will go on the less substituted. So we get the benzylic. But we can get, I had some bromide in configuration. So this would be the E, but then we can also get, because remember opposite, but we can also get syn or Z. Moving on to part 9.7 is hydration of alkynes. Point number 11. What is the acid-catalyzed hydration of terminal alkynes? And describe its reagents. What is formed as an intermediate that's different from applying to alkenes? And how does acid-catalyzed hydration of internal alkynes contrast? We basically learned the mechanism of alkynes will look like this. Now to begin off, if we had an alkyne that looks like this, the reagents we use are hydrogen sulfuric acid and water reacting with mercury sulfate. In process we will form an enol formation, and as a product we will form a ketone. As a ketone. Now, what does this mean? What does this mean? So, let's say we had something that looks like this. Now, this is a different. Forget these reagents. We know the reagents we need to use for hydration of alkynes. Hydration of alkynes. So if you had something symmetrical like this, the mechanism will start off with the alkyne triple bond trying to deprotonate something like an acid, like sulfuric acid. This will jump like that. Now obviously we will form the alkene, and note that Markovnikov will happen, but it doesn't apply to internal. So let's say it happened there. We will get E opposite, or we could also get sin. And so if this is the case, what will happen next? We learned we could use the water now, and H2O, what will it do? It will basically grab this and we will dump the electrons onto, sorry, is that what just happened? Oh yeah, I'm sorry. Hydrogen does not deprotonate the hydrogen. Oh sorry, water does not. Water does a nucleophilic attack. The electrons entered there. Water attacks the carbocation. What does it do? It basically, on the trans, remember, we can get something that looks like this. You can get something like that. Is that correct? And basically all you will do is we will try to make this into what we call an enol. This one we saw here, that was considered an enol because it has the alcohol. So we will grab another water molecule, deprotonate that this time. Okay, grab another water molecule, deprotonate this time, dump it onto the oxygen, and neutralize the compound of our interest. Now, in this case, what will happen is, let's say we were to proceed with, Alright, something I need the correction of is the key doesn't show us the formation of the syn, and I assume it's because of sterics, and so because of sterics we probably would not do the syn. This is not what happens here. It only applies to the trans. Actually it might be better if so just cross this out. We are only going to focus on the trans because trans is where it does all the fun stuff. Basically, this what will happen is this will form into this intermediate. This intermediate is very important. Okay, so these, because it's internal symmetrical, it looks like that, and this will here look like that. So this is called an enol. Enol is important. It's very reactive. Anols are very reactive. Now, what does the mechanism do from here? Basically, anols will want to, the lone pairs on the electrons here will want to donate, push it down here, and basically this alkene bond will want to protonate or deprotonate part of the sulfuric acid or hydronium ion. Hydronium ions are made because we have excess water and sulfuric acid, and basically when those two are in the mixture, you get hydronium ions as well, which is another strong acid. So you could use sulfuric acid or hydronium ions, which neutralize that into water. And basically this considered mechanism will make it look like this. We will still have the plus, we will form that plus charge basically, and we should get something that looks like this. Now if this looks very familiar, it should be because we are getting there. Water will deprotonate this hydrogen, dump it off, and now what we get here is, let's see, 1 2 3 4 5 6, 1 2 3 4 5 6, and 1 2 3, so we will get a ketone. Basically what we learned from my mechanism was that if we start off with an alkyne, this is internal in this example, and use hydration of alkynes, which means we react with water, mercury sulfate, and most importantly sulfuric acid, we will get a ketone. Alkenes reacted with these reagents will get an alcohol on Markovnikov, but we learned that in this case we get a ketone. Alkynes react with hydration of alkynes to form a ketone in Markovnikov. But you can't really tell Markovnikov because we said internal alkynes don't really apply, neither do hydroboration, which we will talk about. Now, conceptual checkpoint 9.18. If we had this molecule, use these reagents and mercury sulfate, what will happen if we do hydration of alkynes? We said we will get a ketone. Yeah, a ketone. So it's not an alkene, but a ketone, I told you. Ketone, now, which way will the ketone form? Ketone will look like this. Now it doesn't matter if it's there, if it's here, or if it's here. No, because this is internal, so if we look at in either direction, we will get only this for internal symmetrical alkynes. Symmetrical alkynes. But for terminal alkynes, if we use these reagents, if we use sulfuric acid, water, and H2O, sulfuric acid, water, and mercury sulfate, we will get Markovnikov. Just think of Markovnikov when we think of hydration of alkynes. Now this was point number 11. Point number 12. Describe overall mechanism and what allows for rearrangement. We basically talked about the mechanism. So there's that. Now when we talk about hydroboration looks quite similar, but quite different. Hydroboration, we will use base catalyzed tautomerization, but its reagents are the following: BH3 THF followed by peroxide and sodium hydroxide, and we will use anti-Markovnikov, and this is for alkynes as well. And what we get is also ketones like above, except that this is anti. But then we know internal alkynes don't really care about either Markovnikov or anti-Markovnikov. Doesn't care. Let's do an example, conceptual checkpoint. Let's say we had a molecule that looked like the following, and we did hydroboration, BH3 THF followed by peroxide, sodium hydroxide. What will happen? Well, what I think will happen is we have 1, 2, 3, 4. 1, 2, 3, 4. I think you should get this. We should get an aldehyde, because we still have the same number of carbons. If it was hydration, the H2SO4, hydration of alkynes, it would form on the 3, but instead it does on the 4, and this is just an extended hydrogen because it's anti-Markovnikov. Practice. Now, basically this should be, well, easy. What reagents do we do here? We need to know if this is anti-Markovnikov or Markovnikov. Well, we know that this is Markovnikov because this is not a hydrogen, this is a carbon. If we count 1, 2, 3, it goes 1, 2, 3, which means the ketone formed on this carbon, not the terminal carbon, or carbon number 4. So if it's formed between carbon 2s and 4, so if it formed on carbon 3, or this carbon, that means it's Markovnikov. Because if it did on 4, it would be anti-Markovnikov, which is one above. So the reagents we used would probably just be this: sulfuric acid, water, mercury sulfate. Easy peasy. This is part number 13. We will talk about mechanism later. I don't have it in my notes. Do I have it in my notes? No, I do not have it in my notes. Need mechanism. This is for later. Not in notes. On to part 14. This is 9.8. Halogenation of alkynes. Halogenation of alkynes. Turns out, if we have something that looks like this and react it with Br2, or other words X2 in dichloromethane or CCl4 solvent. This is the solvent. What happens? Turns out, as a major product like we observed in alkenes, we will get this as major. It's trans, so it'll be major. But as a minor, turns out we will get small percentage of sin. Mechanism, I don't think it might be well understood, but we will draw one anyways. Let's say we had a terminal alkyne. What we'll do first, if there is Br and Br, it's like that. Consider the mechanism. This will do like share, and then it'll share electrons and then also receive them. Donate that there. Sin fashion, positive charge, and then the Br that belongs, this one belongs here. Negative charge will do a backside attack. Now the question is it more substituted backside attack or less substituted? It'll be more substituted, jumping those electrons there. It's more substituted attack. So we get something that looks like this. Now, if we get the trans, this will attack, do this. We learned how to do with alkenes. So just repeat, jump. And basically we will get similar to what we did. Br still stays there. Plus charge. And we will form that anion. This belongs here. So this, as we learn, become attack, more substituted. Will it be more substituted? Yeah, it will be more substituted. Because this thing is more taking up space. So more substituted, jumps up there. Not sure if it's because of space, but it's more substituted carbon, that's why. And then what you get is okay, also note that here in the top example, these are separate molecules. This was one equivalent. That's why we get this. Here, we're using two equivalents in total of the halogen, or Br2. Two equivalents. So our product now, after doing two equivalents, should look something like this. That's our product. transition state, what will it look like? This is when we're doing our first equivalence. This will be positive here, right? Because when you look back at this molecule, this will also be positive here, but here's negative, because this is where we have the electron-rich nucleophile attack the electrophilic species, and this in relative to this here should be more electrophilic because we're dumping the electrons there. So that's our transition state. .9 analysis. With alkynes, will form carboxylic acids. With alkynes, will form carboxylic acids and CO2. 4 terminal alkynes. Internal alkynes will just be 2 carboxylic acids, but for the terminal, we'll get CO2 as byproduct. Let's do a practice problem. If we had something that looked like this, react with O3 and water, analysis, we should get something like so we had 1, 2, 3, 4, 5. 1, 2, 3, 4. 5. I'm not sure if this is the answer. Plus CO2. I'll check. Alright, turns out this is wrong. Our carbon count ends up on the inside portion. It was a 1, 2, 3, 4. Wait, so we had 1, 2, 3, 4. So then it'll be 1, 2, 3, 4. And then there it goes like that. This is basically what we get. 1, 2, 3, 4. That carboxylic acid. And then we get CO2. Makes sense now, because the carbon on the 5th portion of the alkyne would be this one. That's where the 5 belongs. That is why what should be in place of the carbon goes with these as CO2. Makes sense now. .10 Alkylation of terminal alkynes. Acetylide alkylation. We talked about this in the beginning of the chapter, and idea is if we have something like acetylene here reacted with a strong base and ethyl iodide, what will happen? We'll get ethyl iodide, we'll get there. Deprotonate this, we'll get a negative charge and we get an ethane. This is what we get. 9.10. That was basically it. Now point number 17. How do we convert alkene to alkyne? Now, if we want to do alkene into alkyne, there's a series of steps. This is where we get into synthesis. And if you want to get into synthesis, basically it will look like this. We know we can basically turn this into dihalide. How do we do that? Br2 and CCl4. Because just if you think about it, if we do this, we get, and if we do excess of bromide dehydrogenation, you get Br, 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 Br. How do we do that forward? We can do this now. We can do NaNH2 strong base can double eliminate or excess double eliminate dihalides, and use H2O obviously, and we get that. Br2 and excess, that's how you get 4. And NaNH2 strong base, that. Let's do practice. 9.29. Now, how do we do this? If we want to do that, we could just do acetylide alkylation. If there's a hydrogen here, you could just react with NaNH2 and NH3. Basically that turns it into this. Now what do we do that from there? We can react it with MEI. Okay, I didn't explain this. What does I stand for? It's a good leaving group. We learned earlier in the chapter, good leaving groups. And then if we do good leaving groups, basically what it looks like is this will attack the carbon in between, and the electrons will go on to the good leaving group, or the weak base, stable base. HI, remember, strong acid makes into weak stable base. So it wants that charge. We're not talking about HI right now, but it's relevant because it shows the direction that if it deprotonates, it likes. This is kind of like deprotonating and stable. Basically that's where we could extend it. Chain. But that's not the whole answer, sorry. This is not the whole answer. If that were the case, we're still at alkynes. If we're still at alkynes and methyl group, now we still have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, basically, what do we see? Is this trans or opposite? This is trans, it's the opposite. What do we learn about how do we make trans? We can do this through sodium sulfide and ammonia in liquid form. Ammonia in liquid form. That's our answer. We did how many steps? 1, 2. 3. So we had to go through 3 syntheses. This is the beginning of our introduction to synthesis. Now let's do another practice. B. How do we do this? Well, we learned from our example above that we could turn this into alkyne, not directly, But first we need to turn this into, okay, let's do a carbon count first. We have 1, 2, 3 carbons. How many carbons? We got 4 carbons here. So something's added, but what can add carbon? What can add stuff? How do we add this? First, you need to do an alkyne. Let's take it slowly. So we could turn this alkyne, but if you want to turn it to alkyne, you can't. There's no direct step. We have to first make this into dihalide. How do you do dihalides? X2, or I think we might be able to do HBr, but I'm not too sure, so we will look into that later. X2 and XS. What does that look like? If we do it, this should basically look like say it's BR2, BR, 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 BR. We could do excess Na sodium base, sodium NaNH2 base and NH3 solution. We get that. And here is a terminal alkyne. What can we do with that? We could also do again NaNH2 strong base and ammonia solution solvent. And what do we do? We get that. And now finally we could use MEI. Why? Because we could just add on and do things there. That's our solution. That's it.